purpose of this is to talk about the integration, and we will wind up with the fundamental theorem of calculus, which allows you to calculate the area of some general function, not a special function like a hexagon or something like that, but just some general function that is that can be differentiated. So we start off with the way things used to be done before Newton came along. The graph shows an area. This is a y equals x squared plus 1. And suppose we wanted to think of it as a floor or something like that, and you want to buy some carpet or linoleum or whatever and cover it. So you want it completely covered. And this linoleum is available only in certain widths. So that means in order to cover the whole thing, you have to buy too much. The area, this is called the light box part of maple. The area of each of these little rectangles is going to be the change in x, which is in this case is going to be 1/2 times the f of that the y coordinate of this. So you have this area, this area, this area, this area, and add them up, and you find out how much carpeting or whatever it is you want. And I've done the calculation, and if the equation is y equals x squared plus 1, then the carpeting you want, if you need 4 panels, is going to be 23 over 4. And you can see that it's very complicated as you increase. Suppose I wanted a finer, more accurate estimate. Then you can have, say, 10 slots. And there's the 10 slots. You can see that you're getting closer and closer to the curve, the tops, but you're still overlapping some. Now, in the old days, before Isaac Newton, to calculate this area, they used what is called the method of exhaustion, which is kind of a fancy way of saying limits. Okay, they didn't call it limits then. And remember, this was a time way before calculators, so you had these people computing by hand all this stuff. So it was very time-consuming for anything except graphs of functions that for which you had formulas like hexagons and pentagons and squares and rectangles. So if it was a general function, then you couldn't do it this way. And of course, if you want even more accuracy, let's bump it up to 50, and you can see that you're getting very a lot more accurate. There's still some error, as you can see. Okay, so that's how it used to be done. You would use, like I said, it was called the method of exhaustion, which is a primitive form of limits. So let's go over to the board now, and we'll discuss how it's done in modern times. So suppose you're trying to find the area under y equals x squared plus 1, and x is going to be x is between 0 and 2, which is what I had up there. Then what he does is he sets up a summation of this guy. He sets up a summation of f of x sub I times the change in x sub I. Change in x sub I means delta x sub I means x sub I plus 1 minus x sub I. Okay? So, and what we do is we go from I equals 1 to n, depending on how accurate you want to make this. If you want to make this accurate, you want to fairly accurate, you choose a large n. And if you want it to be absolutely accurate, you take the limit as n approaches infinity of this guy, and the delta x sub i's are going to go to 0, and for all x between 0 and, in this case, 2. A and B is the normal notation, but we have specific numbers here. So now he goes through some very clever manipulations of the sigma notation and taking the limits, and he finds out, if you look on the bottom of page 374 and 375, after some very intricate calculations, he finds out that the area under this curve, I'll draw a picture which this is 1 and this is 2. The area under that curve is going to be 14 over 3. So that's what he comes up with. if you look, if you have your books on page 378, he gets 14/3. But now, and what they did was they actually called it, we're now on page 378, they called this guy, they called this a definite integral. So this is called a definite integral now, on page 378, this summation and limit. On page 378, and this is called a definite integral. And I'm just replicating this. Except we're going to change this 0 to 2. We're going to go 0, 0, and A and B. From A to B. Okay? So if you look on page 378, that's it. He has this exactly. I'll just go ahead and write it again. F of x sub I, delta x sub I, and I equals 1 to n. And the limit is delta x sub I approaching 0, and x between A and B, and n approaching infinity. Okay? So all those conditions are called, and this is called a definite integral. If you look on page 378, he calls it the definite integral, which means you're going to get a number if a number exists. And it's called, and I'm going to write this immediately below this so you can see the analog of this. This is the integral from the definite integral from A to B of fx dx. Okay. The Greek letter sigma corresponds to our letter s, and this is a long s between A and B, and here's the f of x sub I. You can see how they're related, delta x sub I times delta x. And so that's very nice, but you still have to do all that calculations. But here comes Isaac Newton, and he jumps in with a very, this is the fundamental theorem of calculus, and it's on page 370, I'm sorry, page 382, page 382. And what he says is the f of x, the integral, the definite integral of f of x dx from A to B, now page page 392. The definite integral from A to B of f of x dx, where f is some function, is going to be big F of B minus big F of A, where the derivative of big F is the original f of x. Okay? So the problem is you have to find out the big F, the so-called antiderivative, more generally called the integral, the indefinite integral. So let's do our problem, which remember all the work we went through to get our original problem. Let's do it using this fundamental theorem of calculus, and do it this way. And so we're going to take this. Okay, we're going to take the integral of x squared plus 1 dx from 0 to 2. And of course, you know by now the antiderivative or indefinite integral. The integral of x squared is going to be x to the 2 plus 1 over 2 plus 1. That's x cubed over 3. And the integral, the derivative of what gives you 1, that's going to be a plus x. And this is evaluated from 0 to 0 to 2. This is what I call big F of x. Okay? So if you drop in a 0, I'm sorry, if you drop in a 2, you're going to get 2 cubed, which is 8/3, plus, and this is 2. So 2 is the same as 6 over 3, right? And so this is a big F of B, big F of 2. And then if you drop in a 0 for x here's big F of 0, you're going to get 0. So you get the same answer, 6 and 8 is 14 over 3. And it's so much easier than the way we did before. it's so much easier. All you have to do is find the function whose derivative is a given function. It is almost a trivial exercise if you have a simple function. So that was, and that's what's going to happen from now on. Now we're in integration. You'll have to find clever ways to find the function whose derivative is a given function, or the antiderivative, or the indefinite integral. Now, some of you may wonder, well, what happened to the constant of integration? Okay, this isn't a proof or anything like that, but you can assume that you have, you can assume that the constant is going to be the same here and the same here. Okay, so here's a constant of integration here minus it here. So from now on, you don't write the constant of integration if you have a definite integral. It's gone. The answer to a definite integral problem is a number. The answer to an indefinite integration problem is a function.